In this presentation, we define mechanical energy and the two forms of mechanical energy, kinetic and potential, that we will discuss as it relates to work. So energy is basically the ability to do work. So if something has energy, that means that it can do that there's work that can be done on that object. And remember that work is force being applied over some distance. So that implies that if something has energy, you can make something move. Energy, just like work, is a scalar quantity. It does not have direction associated with it. And so I guess in some ways we could think about energy that could be positive or negative, but in general, the energy forms that we're going to talk about will always be positive quantities, but they are scalar quantities. So the two forms of mechanical energy that we're going to focus on are potential energy, which is stored energy, and it's energy due to position or location. So some examples of potential energy is a bow that's stretched has stored energy that can do work on an arrow and causing that arrow to move. A stretched rubber band or a slingshot has stored energy and it's capable of shooting a rock if you're thinking about a slingshot. And then the one that we're going to focus on, so these are both what are called elastic potential energy, right? So they've got some sort of stretching going on. But the one that we're going to focus on is the last one, which is energy due to position above the surface of the Earth. And so that type of potential energy is called gravitational potential energy. And you can take an object, as you know, lift it above the surface of the Earth, and if you release it, then work is being done essentially by the force of gravity, and it causes that object to move towards the surface of the Earth. The other form of energy that we're going to talk about is kinetic energy, and kinetic energy is due to motion. So potential energy, you don't have to have any motion of the object. It's basically stored in some form. Even chemical energy is a form of potential energy, but it's stored due to its position or its location. Kinetic energy, the object has to be in motion in order to have that form of energy. So there's a lot of information on this slide, so I'm going to do some pointing. So the first one that we're going to talk about is the gravitational potential energy. So potential basically means the potential to do work. So by giving an object potential energy or stored energy, we are giving it energy that it can release later to actually do work on the object. So gravitational potential energy is based on an object's height above some reference level on the surface of the Earth. And more specifically, potential energy, which we write as PE, is equal to the work that's needed to lift an object to that particular height above some reference level. So if you think back to a previous lecture, we had an example where Romeo lifted a textbook, a 1 kilogram textbook, above his head some distance d. So in this particular case, we can calculate the potential energy that this object would have if it's lifted through some distance, which is equivalent to some height above its starting point, by looking at how much force we would have to apply to lift it to that position, and then look at the work that's required to lift it through that distance d. So we know that the work is the force times the distance. If we moved this object at a constant speed, then the net force would have to be 0 because there would be no acceleration. So constant speed implies 0 acceleration, and then according to Newton's second law, F equals ma, the net force would have to be 0. So in order to lift this object at a constant speed, the force applied would have to be exactly equal to the weight of the object. So here, to calculate the work, my force is just the weight of the object. And then the distance that the object moves is, we're calling this some height. So it started off at some reference, and I'm lifting it to some height above that starting point. So the distance is some distance h. So the potential energy is equal to this particular amount of work that's required to lift the object to this height h. So we can define the potential energy as equal to this work, which is just equal to the mass of the object times gravity times the height. So the higher that you lift an object above some reference point, the more potential energy it has. So let's just think about this for a second. So if you were to take a book and you pick it up from the floor and you lift it above the floor some distance, you're giving it potential energy. If you let go of that book, it will fall until it hits the floor, and as it falls, it will keep speeding up as it falls, right? So my reference in that case, where I'm starting, is the floor. You could take this same exact book and you could take it and have it on a table, and you lift it to the same height relative to the ground above the table. It also has potential energy, but it would have a different height because I would measure it relative to the table. If I let go of the book could only fall until it hits the table. So I guess what I'm getting at here is that this height h is in reference to wherever your starting point is. So you have to decide, is it relative to the ground or is it relative to the table? So that reference is sort of up to us in terms of where we define that. The path that we take in lifting this book to get to this height, so we could have taken the book and lifted it straight up, or we could have kind of lifted it and moved it back and forth, and it turns out the amount of work required to lift it is still the same. So potential energy, the path doesn't matter. It only depends on where the book started or where the object started. The mass started here, and then vertically it was lifted to this height here, h. And so because it was lifted to that final height h, it has this potential energy. And even if I had taken the book and started here and I whipped it around like this and I still ended up here, it would still have the same amount of potential energy. So of course we know that m, it represents the mass of the object in kilograms. G just represents the gravitational acceleration numerical value, and so we use 10 meters per second squared just because it's a little bit easier, of course, than using 9.8 conceptually for our conceptual understanding. H is the height measured from some reference position, and that's going to be in meters. And so our potential energy units are going to end up being joules. So if you multiply kilograms times meters per second squared times meters, you will get units of joules. So one example, we're going to look at some examples, but one example of potential energy or stored energy is water that's elevated above in a reservoir. And also the previous, in a previous lecture, we had that PhET simulation, which was showing how energy can change from one form to another. And we had water that was flowing, but here's an example of a hydroelectric plant. And so up at the top here, we have the reservoir of water, and it has potential energy because it is raised above some lower position. So it has potential energy, it has stored energy. As the water falls, it loses potential energy, but it causes this turbine to turn, and that converts that mechanical energy that it has into electrical energy, and then that electrical energy can be then transmitted through the power line. So this is just an example of, again, different forms of energy. So potential energy here, mechanical energy, one form of mechanical energy, potential energy that's converted essentially into electrical energy. Okay, so here's one of our quick questions. So I have a 1 kilogram or 10 Newton block that's lifted and pushed up the inclines shown below. In all of the cases, the block rises the same vertical distance of 3 meters. In which case is the potential energy of the block the greatest? So when it gets to the top, in which of these cases is the potential energy going to be the largest value that, in all of these, right? So in the first case, the block is moved straight up and put on the top. Here it's pushed up the incline, and then here's another incline, it's pushed up to the top. So eventually they're all going to reach the top like this. And so the question is, you know, which one is going to have the greatest potential energy? And the answer is that they all have exactly the same amount of potential energy, because potential energy is, we're going to see this on the next slide, but the potential energy is just the mass times gravity times the height, the vertical height. And they all have the same mass in all these cases. Gravity, of course, is the same for all of these, and they all go the same vertical height of 3 meters. Yes, in the second case, it goes up the incline, but vertically it goes 3 meters, and then the same thing here, it has a longer incline, but vertically it goes 3 meters. So all would have the same amount of potential energy. So what is that potential energy of the block for each of these cases? So starting point and ending point here. So we know the mass is 1 kilogram. We know gravity is 10 meters per second squared, and we know the vertical height from the starting point to the ending point is 3 meters, so that gives us a total of 30 joules. So the potential energy for each of these blocks would be equivalent and would be 30 joules. How much work was required to lift the block in each case? Well, we know that by definition, the work required to lift the box, is equal to the potential energy. That's how we defined potential energy. We said that the potential energy is basically the work required to lift the object through some height. And so the work for each one of these cases is exactly the same, which is 30 joules. Which case requires the least amount of force during the lifting? All right, so this one is a little bit harder, but if we think about it, I think it'll make sense. So they all have exactly the same amount of work, right? 30 joules. And the work is the force times the distance. So let's think about it in terms of, are they all covering the same distance when the force is applied? So in my first picture, I have to lift straight up in order to get the block at the top. In the second picture, I have to apply a force along the incline to make it get to the top. And in the third case, also I have to apply a force along the incline for it to get to the top. So we have different distances covered, right? So the first case, I have a small distance. The second case, the distance is a little bit bigger. And in the third case, that distance up the incline is even bigger. So what we know is that the work is the same, but the distances are changing. So as the distance goes up, the force has to go down, right? So these are the force times the distance are inversely proportional to one another if the work is a constant value, right? So if I want to keep this number 30, if I increase this distance, I'm going to have to decrease the force. So it turns out that the third picture, where the force is applied over a longer distance, this force would be less to get the block to the top versus the previous two cases. So the most force would be the first case, and then the second case would be a little less, and then the third case would be the least of all. So if you think about it in terms of just lifting an object, suppose that you were trying to lift a very heavy crate to get it on the back of a moving truck. You would rather not try to lift the crate straight up and put it on the truck, but if you had like a ramp of some sort that you could push the crate up the ramp, and let's say the ramp had little rollers on it, right? So there's no friction or anything, or very little friction, so it's going to make it easier. You would want to push it up the ramp. It's going to be easier to do that versus trying to lift it straight up. So the same amount of work is done, right? Because you still have to get the block to the top. This requires less force, the last picture, but a whole lot more distance. But sometimes, if you're trying to lift that crate or whatever all by yourself, you may not be able to apply this much force. It might be too heavy, but if you put it on that ramp with the rollers, that force that you would have to apply would be much less. This is kind of one example of, I want to say a machine, but like a simple machine example would be an incline. So this is just an animated figure with the same thing. So we have these 3 ramps, right? And it's just showing that when you figure out the work done in each one of these cases, when it gets to that position, they're all going to be exactly the same, right? Their back wheels are all located at the same position where they start down here, and different forces are being applied to get them to those positions. More force, the higher the incline, and the distances are different, right? So in the first case, the distance is much greater, and in the last case, the distance is much less, but the force is bigger, but the same amount of work in each case. Okay, so we know what potential energy is. Potential energy, gravitational potential energy, is energy due to position above some reference. And so now we can define kinetic energy. And kinetic energy is energy due to motion. It's also a scalar quantity. It's always going to be a positive number. And the kinetic energy is 1/2 the mass times the velocity squared, or the speed squared. We could think about it that way. So even if the velocity or the motion was in the negative direction, the kinetic energy would still be positive because we're squaring that velocity term. So of course m here is the mass of the object in kilograms. V is just the speed of the object in meters per second. We have to remember that only the speed term here is squared. So kinetic energy is 1/2 the mass times the velocity quantity squared. So there's no parentheses around, the mass and the velocity here. In terms of units for kinetic energy, it would be kilograms times meters per second for the speed, but that's squared, so those units become squared. Meters squared per second squared. A kilogram meter per second squared is a newton, and then you'd still have a meter left over, so I get joules again. So all of my units for energy, work, all are going to have those same units of joules as long as I use my standard units for mass, kilograms, speed, meters per second, and so on. If an object has kinetic energy, that means it's in motion, and it also has to have momentum. And remember, momentum is just mass times velocity. So, and momentum is a vector quantity. So, and this is also true vice versa. So if an object has momentum, it has kinetic energy, and if it has kinetic energy, it has momentum. One of the things that often gives people a little bit of trouble is if you have the kinetic energy and you want to determine the speed of an object. So I thought it was worth just spending a moment and talking about how you could do that and writing down the formula. So suppose that we were given the kinetic energy of an object and we wanted to solve for the object's speed. So we start off with our expression for kinetic energy is 1/2 mass times the velocity squared. We can multiply both sides of the equation by 2, and that will get rid of the half over here. So I have 2 times the kinetic energy is mass times velocity squared. I can divide both sides by the mass, and it will get rid of the mass term here, and I get 2 times the kinetic energy divided by the mass is equal to the velocity squared, and then I can take the square root. So this formula here is just a nice one to keep in mind. If you're trying to figure out how fast an object is moving and you know its kinetic energy, you take 2 times the kinetic energy, divide by the mass, and then take the square root of that whole quantity. And we're going to use that a little later as we know when we know what the kinetic energy is and we want to know how fast something is moving. All right, so this is again one of those questions. What happens if you change an object's motion? So in this case, if an object's speed is doubled, what's going to happen to its kinetic energy? So this often will trick people up. So again, the best thing to do if you have a question like this is just to throw some numbers in. So we know that kinetic energy is 1/2 mass times velocity squared. So I'm going to say that my object originally has a mass of 2 kilograms and it has a speed of 1 meter per second. And I want to know what happens if the object's speed is doubled. So the mass stays the same, 2 kilograms, and the speed is now 2 meters per second instead of 1 meter per second. So I can calculate what the kinetic energy would be initially if the object was traveling at 1 meter per second. So I have 1/2, the mass is 2 kilograms, and then the speed is 1 meter per second squared. 1/2 times 2 is 1, 1 squared is 1, so I just get a kinetic energy value of 1 joule. So you might have been wondering, why did I use 2 kilograms instead of just using 1? Because when I pick my numbers, I usually pick easy numbers. The reason I picked that was because I knew that the mass of 2 would cancel out that 1, and it would give me a nice easy value here to deal with. So let's go through the same process if the speed was doubled. So my kinetic energy would be 1/2 the mass times the speed squared. So 1/2 2 times 2 meters per second, but the 2 here is squared. So 1/2 times 2 is just 1, so these two cancel. But then I have 2 squared, so it's going to be 4. So the kinetic energy actually increases by a factor of 2 squared. Because I doubled it, it will increase by a factor of 4. So we have to keep in mind that in our formula for kinetic energy, the speed is a squared quantity. So if you double the speed, you actually increase the kinetic energy by a factor of 4. And now that we know that the way that this works, I could say, well, what if I increase the object's speed by a factor of 3? So it started off at 1 meter per second, and I increased it to, so I tripled it to 3 meters per second. The kinetic energy would increase by a factor of 3 squared, which would be 9. So whatever you're doing to the speed, you have to square that quantity, and that's how the kinetic energy would change. If the object's speed is doubled, what happens to the momentum? Well, let's think about going back to the definition of momentum. So momentum is just mass times velocity. So initially, the object would have had a momentum of 2 kilograms times 1 meter per second, which is just 2. If I double the speed, it would be 2 kilograms times 2 meters per second, which is just 4. So the momentum increases by a factor of 2. So when the motion of an object changes, specifically its velocity, the kinetic energy is going to change differently than how the momentum changes, and that's based on how they're proportional. So the kinetic energy is proportional to the velocity, or the speed squared. The momentum is directly proportional to the speed. Going through the same process again, if an object's mass is doubled, what happens to its kinetic energy? So we start off with our same initial conditions, mass of 2, speed of 1, but now our mass has doubled, so it's a value of 4, but our speed has stayed the same. So the kinetic energy is 1/2 the mass times the speed squared, just like before. 1/2 times 2 cancels, I get 1 joule. If I now put in a mass of 4 kilograms, 1/2 the mass of 4 times 1 squared gives me 2. So if I double the mass of an object, the kinetic increases by a factor of 2, or it also doubles. So the kinetic energy is proportional to the mass. So whatever you do to the mass, that affects the kinetic energy in the same way. We could ask the same question about what happens to the momentum if I double the mass. So the momentum would still be mass times velocity. To start with, it would be 2 kilograms meters per second. If the mass increases or doubles so that it's 4, the momentum becomes 4. So this is twice as big as what it was to start with. So the momentum increases by a factor of 2. So if you double the mass of an object, the kinetic energy increases by a factor of 2, and the momentum also increases by a factor of 2. And that's because they are both directly proportional to the mass. Whatever happens to the mass, it also happens to the momentum and the kinetic energy. All right, we've done some examples, but let's just go ahead and do one more example here. So what is the kinetic energy of a car that has a mass of 1,350 kilograms that's traveling at a speed of 29 meters per second, which is about 65 miles per hour? Kinetic energy is 1/2 times the speed squared, velocity squared. So 1/2, 1,350 kilograms times 29 meters per second squared. Only the 29 is squared, and then I can multiply by 1,350 and then times 1/2, and I get 567,675 joules. Could also calculate the car's momentum, which of course is different than the kinetic energy. It's just the mass times the velocity. And so I would get 39,150 kilograms meters per second. So there's definitely a difference between kinetic energy and momentum. But if I have kinetic energy, that means I also have momentum. And if I have momentum, I automatically also have kinetic energy.